So, okay, cool. Are you guys cool if I then continue on? I saw a couple thumbs up. I just want to make sure. All right, cool. So I'll try to do my best not to take too long on this part. But of course, if you guys have questions, like if you guys have questions, you have questions, right? So really quickly, ensemble methods. Oh, forgive me first of all, because I got really excited about doing ensemble methods. So I have a little pictures and little meme stuff. I don't know. I got excited about doing stuff. So ensemble methods. Ensemble means basically a bunch of like things, right? Like think of an ensemble for like a band or something like that. And so does anyone know Captain Planet? Last time I did this, no one knew who Captain Planet is.
No,
I see a couple. Okay.
I
it's like from
see
like
it a lot.
Yeah, I see Captain, a little emoji there. Captain Planet was like, I want to say it's like the 80s, 90s or something like that. It's kind of a corny show. I used to like wake up for like at 5 a.m. and like watch the show because it's already too old for me. But like basically the main premise is that each one of these little characters, it's like the Power Rangers. If you guys ever seen Power Rangers, it's like they each have their own separate like little, I don't know, power essentially, like their ring. And it's not like Power Rangers at all, but they each have this thing and they can combine together at the end of the episode into Captain Planet to basically create this thing where he has all the powers of, I don't know, Earth or something. I don't know. But anyway, ensemble methods basically do this, where basically each one of these guys are different kinds of models, and they each kind of contribute to the full group to make a more powerful model than the sum of their parts. And that's essentially what the idea of an ensemble method is. So we'll talk about things like decision trees, and the different parts like backing and boosting and stuff like this. Yes, Carl, Earth, Fire, Wind, Water, Heart. I've watched too many of those episodes. I don't know if it was ironic or not. I still can't figure it out. But anyway, if you haven't seen Captain Planet, just watch like the title sequence and that kind of give you the whole idea. Anyway, machine learning. We have a couple of methods, bagging methods and boosting methods. So there's a whole bunch of different ways you can think of ensembles, but we'll kind of go through this. And bagging, I think, is the most confusing because bagging makes, in my head, it's like, oh, a bag. Why is it called bagging? It's not because of that. It's called the Bootstrap Aggregation. Basically, it stands for Bootstrap, which hopefully you guys know. Bootstrap basically is like random sample. Like when you hear Bootstrap, think random samples essentially. And aggregation, right? Basically collecting them all together into an ensemble. So essentially what we do, we use random sampling to train the same algorithm and use that to vote on the classification. Note that like if we called this like, if we actually did it without replacement, so remember with Bootstrap, you randomly sample, you pick out like one from the hat, you have like, you know, whatever thing it is, and you put it back in, and then you select again. If you didn't do that, that replacement, put it back in, is actually called pasting. But no one talks about pasting because it's lame. Everyone talks about bagging. All right, so a couple methods. The most famous method is it's a random forest. So you guys all know decision trees, right?
Yeah.
Decision trees. Cool. Decision trees are kind of lame. They're not super strong because they just have a lot of issues with essentially overfitting, and they're deterministic. They're a greedy algorithm where they always decide on the same thing no matter what the, like if you put in data, like the same data, it will always produce the same model, which isn't super powerful because it means we can't find interesting patterns. So what we'll see is that random forest is actually like what's it called? A kind of a taking a decision tree and making many different things and actually creating a really powerful machine learning algorithm. It's actually one of my go-to ones where I want to do like a really quick baseline. It usually performs pretty well without me having to like adjust the parameters too much. But anyway, bagging. So basically we hear things like training weak learners, and know that we say weak. Weak doesn't actually mean like it's not very good. Weak learners could just literally mean like, oh, they're just not as powerful as the sum of its parts of the other learners. Okay, and basically combine it together by by voting. So this I think comes from the curriculum itself. So you guys might have seen this like diagram. You basically have an input, and you bootstrap the actual sample, and you actually pass it on to the models in this decision trees, and actually using those different decision trees. So you can see decision tree model 1, model 2, model 3. These are actually different decision tree structures. And essentially you take that bootstrap sample and train on this bootstrap sample for each decision tree. And so essentially what you do, you have a variety of different decision trees. And then together they say, okay, when you have your prediction at the end of the day, right, feed its prediction, you actually have this new input data. It feeds into the model itself, the random forest in this case, and says, okay, we're going to make all these different predictions. You make all these different predictions here and say, okay, like, what do we vote for? And basically these, like, let's say these 4 decision trees says, oh, it's class A, you know, and this one says, oh, this is class B. And then these 3 say class C, then it's going to be class A. So the idea there is that basically you have more variance versus like a decision tree where it's always going to be the same exact value no matter what. Okay, so kind of going through like what random forest is. So the good stuff is that it's like it's kind of like, I call it like a super friend. It's kind of like each one just part of the decision tree doesn't know a huge amount, but altogether basically it's very robust. So actually it's much more powerful than any individual decision tree within random forest itself. It's really high performance. It has a really low variance, which is like a super big issue with decision trees in general, where we have very high variance, basically based on what data we give it, it's going to perform very differently. So the low variance basically comes from the fact that there's just many decision trees in here. It's also transparent, which, as you guys will find out in like neural networks and stuff, which are black box models. If you guys have heard of black box models, basically you just don't really know exactly why it made the decisions it did. Because each one is a decision tree, you can actually trace back exactly why it performed the way it did. So if, for example, if you are debugging, you can actually look at each individual decision tree in the random forest and say, hey, this one's being weird. Like, what's up with this one? And you can actually look at specifically what is it about this decision tree versus the other ones that's performing differently, which is affecting your random forest. It's kind of like a random forest. I love the play on words. The decision tree have many, many trees having a forest. You can look at a tree as like, if a tree is a disease, you can like get rid of it, or, you know, observe like, why is it disease? Why is it not giving good predictions? Okay, cool. Some bad stuff, right? We got many, many trees to plant. Basically, because we have a random forest, we have many, many trees. It actually has to store each one of these models in the whole random forest. So one is that like you just have so many of them, which makes it computationally expensive to actually create. So when I say computationally expensive, I don't know if you guys have heard this term before, basically means it takes a lot of computing resources, right? It takes a lot of time. It's a lot, and if you don't want to have that time, you give a more powerful computer. That more powerful computer could have been doing other things possibly that would have performed better or just as good with less time, with less resources. So it can get very, very large. Memory, so this is actually the physical space of where you store the trees. If you have many, many trees and you want to have this model, it's already trained, it's all done, you did all the hard work, and you want to put this now on some device that this prediction, you can do that, but you better be able to store all these things. And one of the problems is like, imagine if you have something that's relatively small. Let's say you have this amazing random forest that does a really great job, you trained it on everything like that, but it takes, you know, 10 gigabytes. And it's like, well, like, I'm not going to put that on a phone anytime soon. Like, it's just not feasible. Or, you know, what if you have something that's like a smaller device, which you can like actually deploy it onto something that has a limited amount of memory? It's just not going to be able to fit, you know, a relatively large force. So they tend to be very bloated because it has essentially many, many parts into it. So you guys have done k-nearest neighbors, right? So you can think of the same thing with k-nearest neighbors. It's kind of the same issue. Deploying k-nearest neighbors onto a system, it has to remember where all the data points are in order for it to make its prediction. This has to remember all its decision trees in order to make its prediction. Okay, make sense so far? Cool.
So a random forest is considered part of bagging?
Mm-hmm. That's right, because we're basically doing Bootstrap, where we actually randomly sample across the subspace itself, basically deciding on different features. So if you have like 10 features, not every decision tree will have the same number of features in the same features. So this might only have like features 1, 5, and 8. This one might have only 2, 5, and 6.
Right.
Yeah. All right. So okay, so kind of go and describe that like random forest, subspace sampling method, right? So does anyone know about banana trees? Like details of banana trees? So for the record, banana trees are all clones of each other. So if you guys ever had a banana, you probably ate a Cavendish banana, which is the yellow banana, which, to be honest, bananas are fine, but like, this is gonna, like this, when I found this out, this hurt my heart a little bit, is that banana are clones of each other, and they're actually really susceptible to something called Panama's disease, which is a fungus. Basically, it can just like kill off whole like fields. In fact, we're having this problem now with the banana tree population. But we actually had a different banana that was a better tasting banana. And I say that's like, oh, it's a better tasting banana because it was a better tasting banana. In fact, you guys ever have like artificial candy and like artificially flavored like banana flavored candy? Yes, I'm talking like Laffy Taffy or whatever, right? And eat that. You ever notice like it tastes like, does not taste like a banana? Like it might taste good, but like it doesn't taste like a banana. That's not because like some weird artificial flavor is like wrong. It's because the artificial flavor was based on back in, I think it was the 1950s or 40s when it was designed. It it was based on the previous banana that is now extinct because it was killed off by Panama disease. The reason why is because basically all bananas are clones. There are basically no variety in banana trees. And that's essentially what we're trying to avoid with random forests. We're essentially trying to make different trees, decision trees, so no one tree can be like poisoned by bad data or a bad set of columns and stuff like this. So essentially what we're doing essentially is making new, basically avoiding what the banana issue. Like, I don't know, hopefully that kind of sticks in your head, because like that, when I found out about this, like, oh, like this sounds weird to say this, but this sounds exactly like random forests is how I learned it. But anyway, anyway, little side part for banana trees. Let's see here. So what we need to do is basically have new variety within our trees, right? So essentially what we're going to do is we're going to try to plant up new trees, like create new decision trees. And the way we can do this basically is like these different steps. So the first one basically is take your data and take some of it for validation, right? This is called out of bag, right? And the rest is for training. So the idea there, if you have basically stuff for actual training and then actually using it for validation, right? And then the data for training, the bag, right, is split up randomly selecting different predictors. In different predictors, we should think like columns, right? So basically different columns are different predictors. And essentially what we're doing, we're going to split up randomly different predictors. And then what we're going to do, we're going to basically just do the normal decision tree algorithm with that's different predictors in there. So if you have like, column 1, column 8, and column 9, you use that to train one decision tree, right? And then let's say you have a different tree that's going to have a different random sample, right, of different columns, and you're going to do that for that decision tree. You can do that many, many times. You can have many, many decision trees. In fact, you can recycle some of the same columns. For example, you might have like 185 or 189, and this might have like 2, 8, 10. And so they might share some columns, but they're not going to have the exact same thing. Okay. What we're going to do, we're going to train those trees. We're going to, I call them like growing your trees, right? Using those features. And then we actually take our validation set right here, basically take out those columns used for that previous step, make sure basically that's not going to be used for a validation so we can actually make predictions on there. And then what we're going to do, we're going to basically sample across the data set itself. And basically, like, you can think of it almost like, this is my little analogy, it's like your data is kind of like the soil and the different kind of water and stuff like that, essentially seeing how well it performs using these certain predictors. And you can imagine the different predictors as being like different kinds of trees, okay, and see how well that performs. And the idea there is that we'll actually have, no one tree is going to do very well, but them together, basically we'll have more variance between the two and more robust, essentially, instead of overfitting and stuff like this. So random forest is actually pretty good at like not overfitting on the data itself. Okay, that makes sense, people? Any questions? I kind of went through this pretty quickly, but in general, if you kind of think about it, like, oh, a random forest is a bunch of different trees that have different predictors and then basically trained across with your data.
Is that what the OOB score does in the random forest classifier? There's like a parameter called OOB score.
That's the out of bag.
Yeah, is that what this is kind of?
Yeah, and that's to see how well it performs overall on these different like decision trees. Because you can actually pull out, if you look into random forest, you can actually pull out the specific decision trees out of the random forest and look at that specifically, which can again be super useful for debugging.
Okay, cool.
Yeah, awesome. Yeah, so less overfitting, right? Which decision trees love to overfit. Think of like the boxy diagrams for overfitting. Let's see here. So again, I kind of show, oh, I think this is actually code. I kind of just basically took the code that was from here as an example. Maybe not. Oh, maybe not. I just showed the link to random forest, but let's just see what this looks like, right? So random forest classifier, I get my iris data, random forest classifier, we do n estimators. N estimators is the estimators each tree essentially. So like, oh, we have 100 different estimators, right? Max depth, this is basically the actual, you could put other parameters that are for the decision tree. So you can actually say, oh, use these different, how deep does the, the decision tree going to go into, like when you actually grow these different trees into different parts. So there are other parameters in here. You can actually see the classifier here. You can see here is that these are all the different parameters that we didn't set, but you could definitely do this. Notice n jobs right here. Does anyone know what, when you say n jobs, what this actually is referring to? A chance? Yeah, so n jobs is actually, because we can train the random forest on a CPU. CPUs usually can have dual core, 4 cores, 12 cores, 16 cores. You can actually specify saying, oh, use multiple cores to train your random forest. So the idea there is that each core on your CPU can train a tree separately, and that way it can hopefully perform better. Note that if you do set this end jobs, know what kind of system you have. If you put like more jobs than there are cores, your computer will end up doing something called thrashing, which basically means that the CPU isn't getting the data, and you likely will kind of like freeze up and will actually take longer than if you didn't specify how many cores to use. So just kind of be aware that if you do end jobs here, you typically want to know how many cores you have. There is a parameter where you do end jobs equals -1, which will then perform however many cores you have. However, I don't suggest doing that if you're not familiar with your computer, because sometimes your CPU might be doing other things. And if it's trying to use everything on there, it might block up some of your stuff. And I've had students talk about, like, my computer freezes up. I'm like, well, yeah, because basically your computer says, oh, ignore you. I don't care whatever CPU process is going there. I'm just gonna go train some trees. So just kind of be aware of this, but it can be useful for speeding up the process.
So with random forest, you don't train test split?
No, you would still do a train test split, because when you actually train it right here, like I didn't do in this case, that's what you probably should.
Okay.
But you should do, like, you should think train test split basically for every machine learning algorithm. Okay, cool. Yeah, so just kind of showing you guys really quickly. Basically, I have this data. I just did it quickly. It's like, oh, just to show you the process. But this is basically your X data. So your X, and this is your Y right here. And then basically, this basically trains it right here, this dot fit. And then I can take, for example, in this case, these are different parameters, or sorry, not different parameters, different, like, for example, let's say the iris data. It's like, oh, I can't remember what the iris is. Like different like widths and like heights and stuff, the petals and stuff like this. So there's like 4 different, like you can think of this as one data point. It's like 0.1, 0.8, 0.3, 0.5. What class is it? And then same thing for this, like 0.1, 0.1, 0.1, and see how well it performs. In this case, it guessed that, or predicted to be 0, 0 as being like, oh, the first data point is class 0. The second one is class 0 in this case. But I could like change this to like different values. If I knew more about the data, I would have specific numbers that I'd put in here, or, you know, your
So 0
test.
is in flower type, right?
Yeah, exactly.
Okay.
Yeah, I'm trying to think, like, trying to get it to guess something different, but I don't know the data well enough to tell you. All right, let's see here. Oh, really cool feature importance. So have you heard about feature importances for random forests?
Yep.
Okay, cool. I see some. That's good. Yes, this is super useful because it basically will tell you essentially, oh, there's some different features. It's essentially how relatively important a given feature is based on the voting scheme, basically saying, like, how well does it perform when you actually try to train these trees, and which trees basically use these different columns like this. So it's gonna be really important. I will tell you guys is that usually what I see a lot of people do, they'll put out feature importance and they'll show like the graph to like non-technical stakeholders, say, oh, here's the feature importance for each of these things. I personally think that's the wrong direction to go, because usually when you're talking about non-technical people, they don't know what those things are. And then usually talking about feature importance by itself, like showing a graph, it doesn't really say exactly, like, what does that mean exactly? Like, this feature is there, and you have to kind of go through a whole explanation and stuff like that, or kind of just like hand wave and say, don't worry about it. So in general, I say, if you do feature importance for a non-technical audience, don't show that graph that you could do. Like, I see it all the time where feature importance, and they show like the different values of what the different feature importance is. It's probably better to be like, hey, these features we found are the most important based on our model, and just like state those are the features versus like trying to show a graph that is likely going to confuse your stakeholders. Yeah, cool. Any questions on random forest? No? Pretty good. All right. Oh my gosh, I'm going through really quickly today. All right, boosting, which is probably the biggest one that is probably the most confusing for most people, but we're going to finish it up in record time. So we'll see how this goes. So the other method is boosting. And so with boosting here, basically it's the idea is that we have a weak learner and we're going to create strong learners, but it's not by taking a bunch of weak learners and having them vote. It's basically trying to iterate on top of the weak learner to make it stronger and stronger and stronger. We use an iterative process called sequential learning, which means that this is really difficult to parallelize, in the sense like where we have random forest, we can train each decision tree separately, like at the same time. It's harder to do this in parallel. There are some packages like XGBoost does this, where they try to do more things in parallel, but basically it ends up being slower in general, because essentially you have to basically rely on the previous learner and then improve on that, and then improve on that, and then improve on that. So it takes some time. There's some kind of different methods, AdaBoost and gradient boosting. So I'll kind of show you guys really briefly on this. To be fair, or to be frank with you guys, do you need to know specific values, like how exactly these things work? Not really, to be quite honest, but it does help to kind of get an idea of like what's going on. Note that gradient boosting, if you see XGBoost is using a form of gradient boosting. If you try looking up the paper, XGBoost, just be prepared to be like really just like eyes get crossed for a while, because it is quite complicated, but know that it's a subset of gradient boosting. Okay. So ADA boosting, I'll kind of just show you guys really quickly. The idea here basically is that if we have our data points, let's say it's two different classes, blue and red, represent this blue and this red minus sign, or yeah, this blue plus sign and this red minus sign, and we're trying to classify it. Basically, let's say we have their first model, and their first model, it's a weak learner, it's just a straight line, just gonna split it in whatever two dimensions to try to separate them out. And it just says, oh, for whatever reason, it says, oh, this is the best way to separate them, right? Doesn't really matter what it is, but like it says, oh, it splits in this way. Basically it says, hey, well, you got some of these right, but you also got these right, you got these ones wrong. And basically what happens is that essentially you adjust the data, the importance of these data points to say, hey, you should care more about these represented by the size. So you kind of like say, hey, you want to, like, because you got these wrong, we're gonna increase the error, this basically decreasing the score, increasing the loss, right? Until basically this is going to be equal. So saying, oh, like now these are going to matter more, right? And then you draw a new, using your same simple model architecture, you make a new model based on saying, oh, these points are much more important. And now you can see like, oh, the blue matters more, right? And it's like, okay, now I got some of these wrong. In this case, these like minus signs, these were wrong. So we're going to increase the error on this guy, on these guys right here, and make a new model right here. You can kind of represent by these like bigger minus signs. And so the idea here is that we kind of keep doing this, and we're not going to get like, because this learner is so weak, it's never going to do a perfect job, right? It's just a straight line cutting either horizontally or vertically. But we're going to combine these together into this guy right here. And in general, what we'll have basically, it's kind of like voting, but essentially what happens is that these learners essentially are being emphasized on different points, basically saying what's more important. And it actually ends up being actually pretty good at making a prediction of something that's relatively close. And you can see here, the whole model itself will actually be this decision line right here. So it's a little more complicated than this original learner. So now we took a bunch of weak learners and actually increased their ability by changing their error values, creating a super learner right here. Okay. Does that make sense conceptually, what's going on here? Yeah. Internally, you don't have to worry too much about it, but like just kind of know that's kind of what's going on here. You can look at the mathematics itself, like why this happens, but we don't need to go into that full detail. And again, just to implement it, it's pretty easy. AdaBoost classifier. It's the same thing as doing any other machine learning algorithm with sklearn. Okay, cool. Some hyperparameters on this, just kind of know that you can do things. You can say that your base estimator, remember that this weak learner right here can be whatever learner you want. It could be a decision tree. It could even be like a random forest or some other complicated classifier. But the idea here is basically you're saying, hey, use this classifier to train on each one of these situations. Okay, so in general, decision tree tends to be us, because decision trees are really quick to train and easy to like adjust and stuff like that. Okay.
So you would use random trees inside of?
You could. You could. In general, you probably use a decision tree just because it's much faster and you're gonna have a smaller model in the end versus using a random forest for every single iteration. Might be too much. Okay. Cool. All right. Sound good? Pretty cool. All right. So last one's gradient boosting, and gradient boosting is kind of like gradient boosting in the sense that it's improving each model, but what it's going to do is basically going to base it on the residuals itself. And I'm going to tell you guys right now, this is a little confusing. I usually have people like, I don't understand exactly what it is, and it takes a while for people to get it. So forgive me if it kind of like hits you with like a brick wall. Like, I'm not sure how this goes. But basically the idea here is that we have, starting off with our model right here. Oh, this is the ground truth. Starting off with our first model right here. Okay. We can see basically like this model, you can see that Y value here. You can see the residuals, right? They're like, it hits some of them pretty well, like this one and this one over here, maybe even, but some of them are really far off. And essentially what we do is we say, okay, here's our first model. We fit a model called F1X, right? So that's our first model. So this blue line is F1, right? And say, okay, these are our predictions. And then we say, okay, get the residuals. We'll call it H1. This is usually the terminology people will see for gradient boosting. H1 is basically how different are those residuals from, like how big are those residuals? And that will be a function based on like, oh, the value that was at 2, the residual was negative, 0.5, right? So basically you have now a function that describes on each x point how big the residuals are, okay? And then what we do, which is the subtle part, we create a new model by saying, all right, take the original model, but then add in the new residuals on there and fit on that value instead of saying, instead of the original data points. And the idea there is that you now have something, if you have a very small residual, right? This new residual, or the very small residual, it already figured it out, so you don't have to change anything. But if it has a very large residual right here, basically you're gonna try to fit along that residual. So you can see here, this X tree basically takes these values and then basically adds in the residuals themselves into here. It's kind of confusing because it's scaled up and down, but you can imagine basically these residuals right here, which are very, very large, are going to be much more exemplified, basically. It's like, hey, these are the ones that are not exemplified, emphasized, and that's what's going to basically try to fit on these residuals. So essentially what you're doing, you're combining the original model in the residuals themselves, the gradient, right, the difference between those two, and saying, all right, fit onto those data points. And then going from there, you say, okay, what are the residuals on there? And you basically fit on these residuals now and keep going over and over and over again. And that's essentially what gradient boosting is. I know it's kind of confusing, but the main idea here is that it identifies saying, hey, these are the residuals that are biggest. Try to fit on these residuals versus the ones that are already close to there. It's like, oh, you don't have to worry about that. Like, essentially, they're very, very small differences. So you tend to get these flatter lines if you use 2 dimensions. Okay, so that's kind of confusing, but the main idea here is that we want to minimize, right? We want to minimize that mean squared error, essentially that gradient. It's, well, not gradient, but like we want to minimize the residuals from the model itself. Okay, you can, I put the link to like the gradient boosting here, including like parts of this is actually adapted from like I talked about the hands-on machine learning scikit-learn. Chapter 7 has a good thing about random ensemble methods, including like gradient boosting. So I'm just kind of show you guys really quickly, and we're kind of over, but I'll kind of show you guys a little quickly what this might look like. So this is me doing it by hand. You wouldn't do this by hand, right? You would do a gradient boosting method and stuff like that. I think it kind of helps a little bit what's going on here. So in this case, I'm just basically making a scatter plot of some random data. It doesn't really matter what these points are, but this is my random data. And you can kind of see, it's like, oh, it looks like a parabola, right? That's kind of what we're going for. I'm going to go ahead and put this into our test and our train and test sets, just so we can keep those separate. And then what I'm going to do, I'm going to iteratively train basically our model and do better and better on each, like based on the residuals. So I'm going to use a decision tree that's relatively quick and easy for us to understand. And so you'll see we'll fit on the XY. So remember, XY is this guy right here. Okay, so I'm trying to fit on this guy. So I'm just going to fit on it. And note that I'm kind of skipping over the train test in this case, but just kind of bear with me. Just imagine this is the training set. So we have X and Y. Say, okay, we had a certain fit, right? Some values are going to be good, some are not going to be so good, right? If I go ahead and say, okay, if I take Y2, which is going to be my new Y, I take the original data, which was Y, minus whatever I would have predicted on there. So essentially taking the difference between the true value and my predicted value, which is the residual, right? So you can actually see Y2 are my residuals. In this case, you can see the closer to 0 I have, the better, right? So this, for example, is pretty close to 0, so that means it's a pretty good point. The ones that are a little bit higher, in this case I have pretty decent ones, but like these higher ones, these means it didn't perform as well, right? And so then what I'm going to do is say, okay, off of these values, these are going to be my new targets, essentially. I say, okay, have my new decision tree regressor. I'm going to fit X, and this is going to be trying to predict the residuals. And so if I do that, and then look at how well it performs on those residuals, I can basically keep iterating over and over and over again. So the idea here is basically like, if you can't, like essentially what's going on is like, if you can't get the actual value, see if we can predict the residuals. If we can predict the residuals, then we can predict how, like essentially how bad it was our first model. Does that make sense? Like if you know how well, like if you have your model and it doesn't do well on certain values, but you can predict what values it doesn't do well on, then you know how well to adjust that model. Does that make sense? It's kind of like I'm trying to think of a good analogy to this. It's definitely kind of a little mind bending right here. But like essentially what's happening is that like we can't do a good job of predicting the very first time, but we can say how far off we are. It's kind of like if you always know you're going to add 1, let's say you're doing some math test and you always know you make a mistake by, like you miss by 10, right? And so, oh, if I know I always miss by 10, I do the whole thing. It's like, okay, just add 10 at the end. And that gives you a better answer. That's essentially what's going on here. Essentially, like, oh, I know I'm going to mess up. So I know how much I'm going to mess up by. I'm going to readjust it. That makes sense? I know, it's kind of, I don't know if that's the best analogy. I see some like worried looks. But the main thing to realize is that if you know how much you're going to mess up by, that's what we're doing the prediction on the regression, or sorry, on the residuals. Then if we know how much we're going to be off by the residuals, then we actually know what the true value is supposed to be. Make sense? Okay. And so basically we do the residuals of the residuals of the residuals and so on and so forth. And that's what that iteration is. It kind of helps a little bit. I make this little plot graph right here. So this right here, I did the whole process of 1, 2, 3. So this is the original data, right? And you can see on the original data right here, and on the right side is the original data. And I can see this green is essentially my first model here. And it's telling me basically how well those, oh, I should, sorry. These are actually representative of the residuals too, of the second model. But you can see this is my first model. And it's doing all right. Some of these points like that are exactly on the line, that means I guessed them pretty much perfectly, right? So that's what this is right here, this red line. And then what I'm going to do is say, okay, well, how far off was I right here? And so, for example, you see how this is like a little negative? That means if I look on that x-axis going downward right here, you can see that's what I see for these data points. Basically, these are negative. And then the ones that are a little above, these a little bit above. These points right here, hey, almost perfect, right? Like, oh, I guess not really because I'm off here. But like these points right here, those are close to 0. I basically have those down. That's what this is right here. And essentially what we do is like, okay, these are my new targets. And now I'm going to train a new a new decision tree on these residuals that looks like this. And then I add this guy to this one, because if I can predict how far off I'm off, like this model is going to be off by like say minus, 0.2, right? And if I can predict, well, you're going to be off by minus 0.2 in this X area, I just add that onto this overall model, the H1 plus H2. Does that make sense? Okay. And then from this model right here, I can see how far off I am. And say, oh, I'm a little bit further off. Like I'm a little bit high. Oh, sorry. I should go with this part. I'm a little bit high off right here, but you can see these ones I did much better. So these should be close to 0, which is what you see. And say, okay, let me make a decision tree based on these residuals from this model, and then add that to this model. So I can do this over and over and over and over again, right? And you can see like basically adding a little bit more, getting the residual, like knowing a little bit more of how far off I'm going to be off the residuals and how far off this model is going to be for its residuals, and adding that in, adding that in. And essentially that's what we talk about boosting. Essentially, we're using what we've learned previously to get to the next part. Does that make sense to people? Thumbs up if that's making sense. Okay, I see some nods. Yeah, I know it's kind of tricky. It bends my mind when I think about it. But I think in general that's kind of like how you should think of it. Okay. But of course you wouldn't do this by hand because this is too much work, right? Instead, what we do basically use something more optimized. In this case, sklearn actually has a gradient boosting. It's pretty easy to use then, right? It's just like every other like machine learning algorithm in sklearn, which is why sklearn is so useful, because it's like, oh, new machine learning model, just do a dot fit and you're kind of done, right? But that's what's going on in the background right here. And though the max depth basically is representing, in this case, a decision tree, right? That's actually what it's using internally. And estimators, right? It's basically saying how many times it's repeating over. And then learning rate basically is just saying, okay, how much should it matter for each one? So in the end, you kind of don't want it to like learn like every single residual, because then you start overfitting and stuff like that. So you kind of want to give it a little fuzz essentially to think how much does it actually matter. So that's what that learning rate basically is. Okay. And so you can actually fit it on here. Note that this basically repeats what we saw above. But in reality, you wouldn't have a learning rate of 1.0 because you wouldn't want to include literally the same weight, H1 plus H2, H3. You probably want to have a decaying part where it matters less and less and less, right? Because we don't want to overfit. So you typically see learning rate much under 1. So in this case, a learning rate of 0.1. And you can see n estimators. I can basically do this 200. But you can see if I run this now, like watch this execution time. This took 8 milliseconds. This is going to take much longer. In this case, 40 milliseconds, so 5 times as long. So you can imagine if it iterates over and over and over and over and over and over again, it can take a long, long time depending on your computer. And you can't really parallelize this because it has to wait for the last one to finish before we go to the next one. Okay, cool. And you can see here, this is the end result. And you can see here, you have more now, a better result right here. And it's still going to be kind of choppy because it's based off decision trees. Okay, cool. Any questions on this? Thumbs up, thumbs down. How are we feeling? All right, I see a couple, I think reluctant thumbs up because it's kind of like, I'm like, oh yeah, I think I got it. But just know basically it's just iterating on top of those, like basically it knows what mistakes it makes. So then it's trying to train off of those mistakes. Now this obviously is doing pretty well, but you want to worry about fitting. This is kind of like an allusion to, not illusion. Yeah, I guess kind of alludes. It's more foreshadowing. It's foreshadowing to neural networks when we talk about early stopping. So we can actually implement early stopping so it doesn't continue on forever. Like let's say I put like, I'll just put something ridiculous here. Let's say 500. Like, yeah, that technically is better, but do you see what, like talking about this overfitting, you can see it's like very spiky. It's like, that's not realistic. We really would like ideally something that's nice and curved, right? So like maybe something, for example, like I'm just gonna put a random number here. Let's say 100. It's like, that's probably closer to like what we'd expect to like what the model really is. We're not looking at those really big spikes and stuff, but basically we have to get more iteration stuff. We're saying, oh, that stuff matters, right? There's ways you can do stuff like learning rate, but one quick thing, again, like hands-on machine learning, scikit-learn, right? That book has a great thing about this. And again, that's where I have like, honestly, like this lesson right here is based around that part of the book. But they talk about XGBoost, it's the same kind of thing. But basically you can start implementing early stopping itself and actually say, hey, at a certain point, if the MSE is too big, right here, if the MSE is basically too small, then you should stop. Like if it's not changing by a huge amount, you're probably starting to overfit because you're basically doing it for the sake of just like trying to get closer and closer. So that's essentially what this is right here. And that's where we can use validation error. So you can see here, you'll see these kind of graphs in general, is that this is validation error. And this validation error is decreasing, decreasing, decreasing as we get number of trees, right? As we kind of reiterate over and over and over again. And as we iterate too much, what's gonna happen is that we're gonna start overfitting on our validation set, right? So, I'm sorry, overfitting on our training set, which we'll see in the validations. Basically, the validation is gonna get worse and worse because it's trying to memorize every single exact point on the training, where in reality, you don't want that. You want something to be generalizable. So this is one way you can actually implement this. In reality, this is probably not what you'd probably do for gradient boosting. Likely you'll use a package like XGBoosting, which you can then put in early stopping, for example, and say, hey, after 2 rounds of iteration, if it doesn't improve or doesn't improve enough, I should really say doesn't improve very much, then you should go ahead and stop. So something to check out there. And that's also, like I said, in this notebook at the end here. Okay, cool. All right. Ooh, that's a long time. Hopefully you guys found that useful. But before we end here, any questions about this boosting methods and all that? Okay, pretty good. Cool. All right. Well, everyone, well, I'll stop it here. I'll make sure to upload this recording, probably be up tomorrow. And that way other people can do it. Or I know we went through a whole bunch of stuff. Again, reiterating, we have that repo. Well, okay, first of all, hands-on machine learning, super useful. I think I sent that in the chat. I'll make sure to share that on Slack too. And then of course, if you have any of the notebooks that we used, it's on this repo right here, which I think I sent in the chat too, but I'll send it on Slack as well. All right. All right, everyone. Well, I should head out. Great meeting you all. Hopefully James is here to help you guys out further, but if you guys have more questions, feel free to message out too.
Thank you.
Thanks.
Bye. Good night.
Good night. Take care.